Okay, this will just be a short demonstration that we will be doing. So, I have already transferred the files to you. So, this is task 5 among the files that I have sent to you. So, in task 4 is about real trace. We can see that if you want. Like CPA you have done on simulated trace. In task 4, actually what we collect in lab, we have done CPA on that. It will take time to show. Like on real trace, it takes around 10 minutes for the whole CPA to run, because we have to do CPA on 4000 traces, and also the number of points are like 100k points are there. So the same thing, it will take time. That is task 4. So if you want, I can give the solutions and files to you. You can see it for yourself, like the difference between the timing of the CPA of simulated and the real traces. And there is a task 6 also regarding DOM that we can see. Like I will give you the codes, you can see it for yourself, like how to write the code for difference of mean attack. So it is significantly smaller as compared to CPA. And now we just concentrate on task 5 is regarding the simulation of fault and the recovery of key using a single byte fault attack. So as sir already explained, I think the single byte fault attack can be summarized using this figure, where we are injecting fault at a single byte of the 8th round, and then this fault propagates to infect all the bytes till the 10th round output. So we will be concentrating on the relations between the fault values in this part. So where we have this in each and every column, we have a relation between all the fault values. So banking on this will be extracting the key byte. So first part of the task is this simulation of the fault, where I will be showing you the complete code, but whatever you are given, where you can complete the code by yourself, or we will be giving you the solutions too. So over here, as you can see, like we have this function for injecting the fault, and there is this function where we simulate the entire AES. So over here we target the 8th round. At the 8th round input, we inject the fault. So we set the byte location as 0. At the 0th byte, we inject it with a random fault. Random fault, as in like over here we XOR it. We XOR the state with a random 8 bit. So this is how ideally we simulate the fault, but in real life scenario, you can have a laser fault, you can have EM fault, you can have clock glitch fault. Like for laser fault, it is quite destructive, because you need to decapacitate the chip. For EM fault, you just it is not destructive, it is kind of a active attack, but you need near field probes for injecting EM faults ideally. Also you need a quite strong amplifier in order to amplify the EM signal, so that the faults get injected at the correct positions if you want. Laser faults are more accurate. You can even create bit faults using laser, as of now we have. And clock glitch faults are just for demo purpose, but for clock glitch fault you need to create glitches in the clock tree of the FPGAs. There are voltage faults, like there are commercial devices available like chip whisperers, where you can create voltage faults, you can create clock glitch faults. Even EM faults are possible in chip whisperer. Like there is a small device known as CW305, where it houses an RTX7 FPGA, where you can create all kinds of faults if you want. It is commercially available, chip whisperers. In the second part of the code, we see like how we actually recover the entire, not the entire key, we concentrate on 4 bytes of the key as of now, but we can ideally recover the entire key if you want. In the first part of the code, what we do is, so let me download the prerequisites. So this is where we create the fault, and we obtain a pair of correct ciphertext, rather 2 pairs of correct ciphertext and faulty ciphertext. So there is a purpose of obtaining 2 pairs, because with a single pair we cannot actually obtain the entire 4 bytes of the key. So we need 2 pairs in order to ensure that the key that we are getting by injecting the fault is the correct key. So, that is why we had to inject 2 faults one by one. So, in order to get a pair of 2 pairs of correct ciphertext and faulty ciphertext. Now, what we need to do is like we input this pair over here of this correct ciphertext and faulty ciphertext, and in this part of the code, if you see like from line number 92 to till the end, where from line number 91 to 126, what we do is like the relations between the columns that we were banking on, we exploit them in order to find the key bytes. Like we guess the fault value from 1 to 256, as 0 is not possible, then we guess the key bytes. Now, based on the guess of the key bytes, we evaluate these relations over here. Like as you can see, we evaluate these relations iteratively one by one in order to get the 4 key bytes, these 4 key bytes for a single pair of correct ciphertext and faulty ciphertext. Now, for the second pair of the correct ciphertext and the faulty ciphertext, we again get a pair of key bytes, and based on the intersection of the key bytes that we are getting, we end up with the correct key bytes that we want to, that we were targeting rather. So, if I execute this, yeah. So, these are the fault values that, or these are the not fault values, rather these are the key bytes that we are getting of the last round. What we are targeting is the last round key that we are getting. Now, if we want to verify the last round key, like of the AES that we have been running, so this is the last round key. So, if you match between these two, we will be able to see that the exact 4 bytes that we are targeting, we were able to obtain that. So, there is a small demonstration of the DFA that we are targeting. So, you can test this with, we have given other fault values, like these fault values were obtained using clock glitch on a basis 3 board. So, we have a basis 3 board in our lab where we were able to perform clock glitch experiment on that and obtain this correct pair of correct ciphertext and faulty ciphertext. So, you can experiment with these values also, but the key that we will obtain will be different where. So, if you experiment with these pairs, so it will be a different set of keys that we will obtain from these values of ciphertext. So, this is the original key that we had in our basis 3 implementation. So, if you have any questions, okay.
When I am playing, it is showing 0x0 in all 16.
Yes, because you did not edit the code, right? Did you edit the code? So, you have to write the correct code, then only you will be able to get the output. I will give you the solutions, so you can consult that, or you can do it also yourselves also.
Then we have to modify if your code where it is.
You have to modify the expressions, like if you see, like I think these parts are where you have to write your code, right?
Like key 0.
So, you have to figure it out which expression you need to. So, it is not that hard, but you need to know the equations in order to do all this. Yeah. Okay. So, thank you.